The cosmos is vast. Among the greatest mysteries are black holes. Imagine a place where gravity is king. So powerful not even light can escape. These are objects of immense density. They challenge our understanding of space and time. We see stars, planets, and galaxies, but some things remain hidden. Black holes are the universe's ultimate vanishing act. For centuries they were just theories. Now we know they are real, and everywhere. Our journey into black holes pushes the boundaries of physics. What are these strange objects? How do they come to be? What happens if you get too close? Understanding black holes helps us understand the universe. From the death of giant stars to the hearts of galaxies, black holes play a crucial role. They are not just destroyers, they are also creators. Let us begin to unveil these dark secrets. Peeling back the darkness. So, what is a black hole? Think of it as a cosmic trapdoor, a region in space where gravity is incredibly strong. Imagine squeezing a mountain smaller than a grain of sand. All its mass is still there, creating immense gravitational pull. This gravity is so intense nothing can escape. Not a spaceship, not a beam of light. Light travels incredibly fast, but even light is trapped by a black hole. That is why they are called black. They don't reflect or emit light. It is like a bottomless pit in space, but not empty. It contains all the matter that fell into it, squeezed down to a tiny point called a singularity. We do not fully understand singularities yet. Our laws of physics break down there. Think of a bowling ball on a trampoline making a dip in the fabric. A black hole is like that, warping space-time around it. Anything that gets too close rolls down into that deep well and cannot get out. This is the power of a black hole. Where do these cosmic monsters come from? Many black holes are born from massive stars. Stars much bigger than our sun. Imagine a star at least 10 to 20 times more massive. These giant stars burn through their fuel quickly, shining brightly for millions of years, but their end is even more spectacular. When a massive star runs out of fuel, it can no longer support its own weight. Gravity takes over and the star begins to collapse. This collapse triggers a massive explosion called a supernova. The supernova blasts much of the star's outer layers into space, forming beautiful nebulae. But what about the star's core? If the core is massive enough, gravity will crush it completely. The core keeps shrinking until it becomes a black hole. A stellar mass black hole is born. Its gravity is now so strong, it is sealed off from the rest of the universe. A silent monument to a dead star. The star is gone, but its gravity remains, in the form of a black hole. This is the birth of an ordinary black hole. Stellar mass black holes are not the only kind. There are also supermassive black holes. These are the true giants of the cosmos. They are millions or even billions of times more massive than our sun. Imagine the mass of a billion suns packed into a region not much larger than our solar system. These titans reside at the centers of most large galaxies. Our own Milky Way galaxy has one called Sagittarius A*. It is about 4 million times the mass of our sun. We cannot see it directly, but we can see its effects. Stars orbit around it at incredible speeds, indicating something very massive there. That something is a supermassive black hole. How do these supermassive black holes form? That is still a big question. They are too big to have formed from a single star. One idea is that they started small and grew over billions of years by swallowing gas, dust, and even other stars. Another idea involves mergers of galaxies and their central black holes. It is likely a combination of these processes. These cosmic titans shape their host galaxies and influence star formation. They are fundamental to how galaxies evolve. The edge of forever, understanding the event horizon. Every black hole has a boundary, a point of no return. This boundary is called the event horizon. It is not a physical surface, it is an invisible line defined by the black hole's immense gravity. Once you cross this line, there is no turning back. Think of a river flowing towards a giant waterfall. Far from the waterfall you can swim away, but as you get closer, the current gets stronger. There comes a point where the water flows faster than you can swim. The event horizon is like that edge. It is the point where the escape velocity becomes greater than the speed of light. Inside the event horizon, all paths lead to the center of the black hole, the singularity. Space itself is flowing inwards, faster than light. The event horizon marks the limit of our observable universe. We cannot see anything that happens inside it. The size of the event horizon depends on the black hole's mass. More massive black holes have larger event horizons. The event horizon is the ultimate cosmic frontier. Spaghettification and beyond. The ultimate cosmic plunge. What would happen if you fell into a black hole? Let us imagine this terrifying journey. As you approach the black hole, strange things begin to happen. The first thing you would notice is the tidal forces. These are the same forces that cause tides on Earth, but a black hole's tidal forces are extreme. Imagine you are falling feet first. The gravity at your feet would be much stronger than the gravity at your head. This difference in gravitational pull would stretch you like a piece of spaghetti. This process is called spaghettification. You would be stretched longer and thinner until you were torn apart, atom by atom. For smaller stellar mass black holes, this spaghettification happens outside the event horizon. But for supermassive black holes, it is different. Their event horizons are much larger and the tidal forces at the event horizon are weaker. You could actually cross the event horizon intact without immediately being turned into spaghetti. But once inside, your fate is sealed. You would continue to fall towards the singularity. Time itself would behave strangely. It is a journey into the ultimate unknown. Shadow catchers, how we actually find black holes. Black holes are, by their very nature, black. They emit no light of their own. So how do we know they are there? We cannot see them directly, but we can see their effects on their surroundings. It is like detecting the wind. You cannot see the wind itself, but you can see leaves rustling or trees swaying. Astronomers are cosmic detectives looking for clues. One way is to watch stars. If a star is orbiting something invisible and very massive, it might be a black hole. We can measure the star's speed and path. This tells us the mass of its unseen companion. If the mass is too large for a normal star or a neutron star, then a black hole is the most likely culprit. Another clue comes from material falling into a black hole, forming an accretion disk. The material in the disk gets incredibly hot and glows brightly, especially in X-rays. This tells us a black hole is likely feeding. Galactic anchors. The importance of black holes. Black holes might seem like purely destructive objects, devouring everything that comes too close. But they play a surprisingly important role in the universe. They are not just cosmic vacuum cleaners, they are also cosmic architects, especially the supermassive black holes at the centers of galaxies. They are fundamental to how galaxies form and evolve. The immense gravity of a central supermassive black hole can influence the stars and gas throughout the galaxy. It acts as a gravitational anchor, helping to hold the galaxy together. When black holes feed on gas and dust, the energy released can have a profound impact on the host galaxy. This feedback can regulate star formation. Sometimes the jets and radiation can clear out gas, preventing new stars from forming. Other times, they might compress gas clouds, triggering bursts of star formation. Understanding this relationship is key to understanding how galaxies like our Milky Way came to be. Black holes are also natural laboratories for testing our most fundamental theories of physics. These dark enigmas illuminate our universe. Future frontiers, continuing our black hole quest. Our understanding of black holes has grown immensely, from theoretical curiosities to observed astronomical objects. But there is still so much more to learn. Many mysteries remain unsolved. What exactly happens at the singularity? Do our current laws of physics hold true there? Or do we need a new theory? How did the first supermassive black holes form so early in the universe's history? Did they grow from smaller seed black holes? Or did they form directly from massive gas clouds? The James Webb Space Telescope is helping us peer back to the dawn of cosmic time, searching for clues about these ancient giants. New tools are revolutionizing black hole research. Gravitational wave observatories like LIGO and Virgo can hear the ripples in space-time created when black holes merge. This gives us a new way to study them, to measure their masses and spins, and to test general relativity in extreme conditions. The Event Horizon Telescope continues to improve, aiming to capture even sharper images of black hole shadows. The quest to understand black holes is far from over. It is a journey that takes us to the edge of knowledge. Each new discovery opens up new questions. The cosmos still has much to reveal.